Hello everyone, here the question is an ideal gas with pressure P, volume V and temperature T is expanded isothermally to a volume 2V and a final pressure Pi. If the same gas is expanded adiabatically to a volume 2V and the final pressure Pa, the ratio of a specific heat of the gas is 1.67 given the ratio of Pa upon Pi 1 or you can say Pi is. So we have to calculate the ratio of Pa upon Pi. So the product of PV remains constant in isothermally. Here, product of PV remains constant. Remains constant in isothermally. Isothermal process. Sorry, in isothermal process, and PV gamma remains constant in adiabatic, and PV gamma remains constant in adiabatic process, right? So for isothermal, we can write here for isothermal expansion P into V is equal to Pi. For here it is given that isothermal for final volume is 2V and final pressure is Pi. So we can write here Pi into 2V, right? So from here Pi is equal to P upon 2 because V to V cancel. So it gives P upon 2, right? And for adiabatic, we can say for adiabatic expansion PV gamma is equal to PA into 2V gamma. So from here PA is equal to P upon 2 gamma, right? And we know that in adiabatic the value of gamma is equal to 1.67. So here put the value of gamma, so P upon 2 by 1.67, right? So we have to calculate the value of Pa upon Pi, the ratio of Pa upon Pi. So the ratio of Pa upon Pi. So it is Pa is upon our P by 2 to the power 1.67 and Pi, so it is written as 2 by P, right? So it gives P to P cancel and it gives 1 upon 2 to the power 0.67. After solving this we get 1 upon 2 to the power 0.67. So this is the ratio between Pa and Pi. Thank you.
Hello students, today our question is curves A and B. In the figure shown, PV pressure volume graph for the isothermal and the adiabatic process for an ideal gas here. So the isothermic process is represented by curve A. So A and B is this and P and V. We have to find this statement is true or false here. So the solution of this question is, we have slope for adiabatic curve gamma is equals to, we have the slope of A is equals to gamma and minus gamma, and this is P by V, that is pressure divided by volume, and slope for isothermal curve M of isothermal is equals to This is for adiabatic and this is for thermal here. So value of gamma is always greater than 1. So from this we can say that slope for thermal curve must be greater than slope of adiabatic. So from this we can say that given statement is true here. So this is our answer for the question. So we can mark it. So this is true here. Thank you.
Hello everyone, a metal of mass 1 kg at constant atmospheric pressure and at initial temperature 20 degrees Celsius is given to a heat of 20,000 joule. Find the following: first, change in temperature; second, work done; and third, change in internal energy. Now we have to find that the change in temperature and mass given here, this is equals to 1 kg, and we know that for the first part we have to find that the change in temperature, and we know that the heat is given, heat, that is Q is equals to written as ms delta T, and we have to find that the change in temperature. So delta T is the change in temperature, therefore change in temperature, that is delta T is equals to Q divided by ms, and Q is given here, that is the value of Q is equals to 20,000 joule. Now we put the value, this is equals to 20,000 joule, and divided by mass is 1 kg, and the specific heat, this is equals to given here, and this is 400 joule per kg per centigrade. So this is divided by 400, and we get this value is equals to 50 degrees Celsius. So change in temperature is equals to 50 degrees Celsius. Now second, we have to find that the work done. So first we calculate that the value of delta V, and we know that work done W is equals to written as P into delta V, and we know that delta V is equals to written as that is this is equals to original volume into gamma into delta T, where gamma is the cubical expansion and the value is given here, and this is equals to volume, and volume can be written as, and we know that density is equals to mass by volume, so volume is equals to mass by density. So mass is 1 kg and density is equals to 9,000. So and gamma, value of gamma is given here, that is this is equals to 9 multiplied 10 raised to the power minus 5. So this is 9 multiplied 10 raised to the power minus 5, and the value of that is the delta T, and delta T is 50 degrees Celsius, and on solving we get this value, and this value comes out, this is equals to 5 multiplied 10 raised to the power minus 7, and this is meter cube. Now the work done can be written as W is equals to P into delta V, and P is equals to that is 10 raised to the power 5, and this is Newton per meter square, multiply delta V, so it becomes 5 multiplied 10 raised to the power minus 7, and the work done comes out, W is equals to that is 0. This is equals to 0.05 joule. So this is the answer. And for the C part, that is the change in internal energy. So change in internal energy can be written as that is delta U. Delta U is the change in internal energy. Change in internal energy, that is delta U, and delta U is equals to written as that is this is equals to delta Q minus work done, and delta Q, that is this is equals to heat, so this is 20,000 minus, and work done is equals to also in joule, so this is 0.05, and we get this value, and it comes out that is 19,999.95 joules. So this is the change in internal energy. I hope you understood. Thank you.
The question is given a monoatomic ideal gas 2 moles is taken through a cycle process starting from A as shown in figure. The volume ratio are VV is upon VA is 2 and here VA is equal to 4. So if the temperature TA at A is 27 degrees Celsius, so calculate here the temperature of gas at point B and heat absorbed released by the gas in each process, the total work done by the gas during completed cycle. So here this is the diagram and here we have to find temperature, heat absorbed and release and total work done. So here firstly we see here the question is given temperature for the given cycle process is here we can write VV upon VA is equal to 2 and here VD upon VA is equal to 4 and here temperature TA is equal to 27 degrees Celsius. So here we can write a Kelvin. So here this is a 300 Kelvin. Now here we take a first process. This is a AB process. Here we take AB process and AB process is a straight line. So that means V by T is equal to constant because this is a linear graph. And here ideal gas equation we can use here PV by T is equal to constant. That means pressure constant. So here AB process is isobaric and pressure is a constant. So we can write here process AB isobaric. Pressure constant. So here we can write this is the VV upon TB is equal to VA upon TA and here this is equal to TB is equal to VV upon VA and here this is the TA. That means here it is equal to 2 into 300 K and here it comes 600 Kelvin. So now here we see the temperature of gas at point B is 600 Kelvin. Now here we process here complete. This is the heat release and absorbed. So here this is the complete cycle A to B, B to C, C to D, D to A. We have to find the heat absorbed and released. So here we take this is the V part. So here we have to find A to V, V to C, C to D, and here D to A. So here this is a we can write A to V is the isobaric process. So here isobaric and here this is the isothermal and here this is the isochoric and this one is the isothermal. Isobaric expansion work, isothermal is expansion work and isochoric is the compression and here isothermal is the compression work. So here firstly we take A to B part here process A B process. So here this is a isobaric. So that means this is a pressure is constant. So here we can write here AB in process of AB, we find heat. So here this is equal to NCP delta T. So here we can put N is equal to 2 and Cp is a monatomic. So here 5/2 and here delta T is 600 minus 300. So here it will come 300 Kelvin. So now here heat in process of AB is 1500 R. That means it heat absorb. Now similarly we take second part here. This is a BC process. Now here temperature is constant and this is the isothermal process. So here delta T is equal to 0. That means and interchange energy here delta U is also 0. So now here D delta Q is equal to delta W. So here heat energy Q is we find here right 2.303 nRT log of volume final and here initial, and this will come the VFB initial final value is here because of VD upon we take a BD will be here 2. Now in question is given here VD and VB. So here it calculates. So that means it's equal to 2. Now here we can put. So here we can write 2.303 into 2 into R into 600 and here log of a base 10. This is a 2. So after calculating this term will come 831.8 R. This is the heat QBC and here also heat absorbed. Now here we take a CD process. That means isochoric process. So here work done W is equal to 0. Now here Q is heat is NCV del T. So here we can write 2 into Cv value is 3/2 because this is a monatomic ideal gas and here Ta minus Tb. After calculating this term will come 3R into minus 300 and here it is equal to 900 R. So that means heat release. Similarly we take process dA. Now here this is a isothermal, so temperature constant, so del U is equal to 0. Now here this is a heat is equal to work done. So here Q is equal to nRT log of base N V final V initial. So here in that case we take a VA upon VD, so that means it is equal to 1/4. Now here we calculate this term 2R into 2.303 into 300 log of 1/4. Now here after calculating this term will come 831.8 R. That means heat, this negative sign here we can write it will come here. Here this is the log of a base 1/4. Log of 1/4 here. Here we take this is a minus log of 4 and here we can write this is a minus 2 log of 2. So this here negative sign will come. So now this is a heat process in a second part. Now here we have to find the total work done by the gas during complete cycle. So here part we can write total work done in a complete cycle. So here we can write a cyclic process is equal to total internal change energy always equal to 0. So here we can write del U net is equal to 0. Now here that means here heat is equal to work done equal to work done. Now here we find del W is equal to in the heat of QAB plus QVC plus QCA plus QDA. Now here we can put the value 15 in first case, 1500 R, and in second case this is the 831.8 R, and here in third case this is the 900 R, and in this case this is the minus 831.8 R. After calculating this term will come 600 R, means this is the work done. This is total work done by gas during complete cycle. So this is the solution. So here we find in process of QDA this heat is released, and here the heat also released in process of CA, and here this is the heat absorbed in case of BC, and here in case of AB process this is also heat absorbed, and here temperature of gas at a point B is 600. So this is the solution to this question, guys. Thank you.
The question is 2 moles of an ideal monoatomic gas is taken through a cycle ABCA as shown in the PT diagram. So during the process AB, pressure and temperature of the gas vary such that PT is equal to constant and T1 equal to 300 Kelvin. So calculate, first part is the work done on the gas in the process AB. Second part is the heat absorbed or released by the gas in each of the process. Give answer in the terms of gas constant R. Okay. So at the first we will talk about the process AB. If we talk about the process AB in this diagram is given in the question. So we know very well that PT is equal to constant, that is given in the question. Okay. So differentiating this equation, we get P as it is, differentiation of T will be dt, plus T as it is, differentiation of P will be dP, that is equal to 0. Okay. So consider that this equation is first. Now if we talk about the equation of state, so the equation of state is PV is equal to nRT, and in the question given that 2 moles, so N is equal to 2, so PV is equal to 2RT. Okay, so we can say that P will be equal to 2RT divided by volume of the gas. Okay, so after differentiating this equation, consider that this equation is second, so differentiate this equation, we can say that dV into P plus VdP, so that will be equal to 2R, and the differentiation of temperature will be dt. Okay, at the first take V at the side of P, so after this we can say that PdV plus VdP that will be equal to 2R dt. Okay, now put the value from first equation in this equation, so we can say that 2RT upon V. Okay, not from the first equation, actually the value of P should be putting here. So P 2RT by V, and dt is as it is, dV is as it is, plus TdP, that will be equal to 0. Okay, so after this we can say that 2RT dt plus VTdP, that will be equal to 0. This is T. Okay, this is T. I'm making it again. So this is nothing but the T. This is T. Okay, so now we can say that VdP, that will be equal to minus 2R dt. Okay, so from this equation we can say that minus 2R dt plus VdP, that will be equal to 2R dt. Okay, we are putting the values from the equations. Okay, nothing else. After this, if we solve this equation further, so we can say that PdV, that will be equal to 4R dt. That will be equal to 4R dt. Okay, take this 2R dt in this side, so VdP is equal to 4R dt. Okay, so after this, if we talk about the part number A, if we talk about the part number A, so we can say that part number A. Okay, so we can say that if we have to find the work done in the process AB, so the work done in the process AB, that will be equal to integration of PdV. Integration of PdV. So this will become, the limit of the integration is from 600 to 300. And what is the value of PdV? The value of PdV is 4R dt. So put the value of PdV here. So 4R dt. Okay. So 4R is constant and the integration of dt is t. The limit is 600 to 300. So that will become minus 1200 R. Okay. That will become minus 1200 R. So this is the work done. This is the work done. Okay. Now we talk about the process number B2C. If we talk about the process number B2C, so it is an isobaric process because the pressure is constant in the process B2C. Okay, so the Q will be QBC will be equal to NCP delta T. NCP delta T, where N is the number of mole and Cp is the specific heat capacity at constant pressure. So N is 2, and what about Cp? Cp will be 5R upon 2 because there is a monatomic gas. So Cp is fixed. And what about the temperature difference? So that will be 600 minus 300. Okay. So this will become 1500 R. If we solve this, so we get 1500 R. Okay. Now, if we talk about the part number 2, process C2A. If we talk about the process C2A, so C2A is a isothermal process. Okay, because the temperature in the process CA is constant. Okay, and as we know that the potential energy, internal energy is the function of temperature. So we are seeing that the temperature is constant. So the internal energy, change in internal energy will be equal to 0. So by the first law of thermodynamics, QCA, that will be equal to delta U plus delta W. Okay, or WC2A, we can write it as. Okay, so we are seeing that delta U is equal to 0 in this question, in this part. So that will be equal to WC2A. Okay, is equal to QCA. Okay, so we get this equation. Now, if we talk about further, so WCA in the work done, if we have to find the work done in the process CA, so that will be equal to nRT ln PC divided by PA. ln is nothing but a log based E. Okay, so put the value of these all. So we can say that this will become a number of mole will 2, R is R, temperature is 600, ln is ln. And what about the PC? So PC is 2P1 in the given figure and PA is P1. So we can say that P1 and P1 are cancelled out. Okay. So the work done in the process CA will be equal to 1200 R ln2, 1200 R ln2. So this is the work done in the process CA. Okay. So this is the process. This is the work done in the process CA. Now again, if we talk about the process A to B, if we talk about the process A to B, so by the first law of thermodynamics, we can say that QAB is equal to delta U plus W A to B. Okay. So this will be equal to NCV delta T. The internal energy will be NCV delta T. CV is the specific heat capacity at constant volume plus W A to B. Okay. So now the number of mole is given, that is 2. And for monoatomic gas, CV is 3R by 2. It's a fixed quantity. And what about the temperature? So temperature is 300 minus 600. Okay. and the work done in the process AB, that is 1200 R. Okay, so now solve this equation. We can say that this will become minus 900 R and this is minus 1200 R. So they will add together, it will become 2100 R. Okay, so this is the answer for our second part. Okay, so this is the solution of the whole question. Thank you.
इस क्वेश्चन में हमें गिवन पीवी साइकिल को, ये जो कंप्लीट साइकिल है जो कि क्लॉकवाइज है, इस गिवन पीवी डायग्राम से हमें इन चारों क्वेश्चन को आंसर करना है। तो पहला क्वेश्चन है द वर्क डन बाय द गैस। जो ये कंप्लीट साइक्लिक प्रोसेस है, इसमें नेट वर्क डन कितनी हो रही है। सेकेंड पार्ट कहता है द हीट रिजेक्टेड बाय द गैस इन द पाथ C to A एंड द हीट एब्जॉर्ब बाय द गैस इन द पाथ A to B, ये कैलकुलेट करनी है। थर्ड पार्ट है द नेट हीट एब्जॉर्ब बाय द गैस in the path B to C, and the fourth part is the maximum temperature attained by the gas during this whole cycle. So we'll start from part A. So the net work done by the gas is equals to the individual processes, because ये complete cycle 3 different steps से मिलके बना है, तो हम तीनों step का different work done निकालेंगे और उसे sum करेंगे to get the net work done. So work done during the path AB plus work done during the path BC plus work done during the path CA. So अगर आप path A to B देखेंगे तो it's an isochoric process and the work done during the isochoric process is 0. And work done from B to C. So clearly हमें मालूम है in a given PV diagram, work done from B to C can be calculated as the area under the B to C curve. So that is area under this shaded region that I am shading with the red pen. So clearly it's an trapezium, and since it's an expansion process, that is work done by the system in which the volume has increased, therefore it's considered as negative by the convention of chemistry. So half into area of trapezium is half into sum of the parallel side, that is 3 P naught plus P naught. That is sum of the parallel sides into distance between them, that is V naught. So this is the whole magnitude with sign of the work done in the process B to C, and the work done from C to A, as you can clearly see, it's a compression, that is work done on the system in which the volume has been decreased, and the work done from C to A is the area that I'm shading with this black pen. It's clearly in a square with length P naught and breadth V naught. So the work done in the path C to A is positive P naught V naught. So on further simplification, you will get net work done as minus P naught V naught. So that is the answer for the path A. Now coming to the part B of the question. The heat rejected by the gas in the path CA. If you see the path C to A, it's clearly a compression. So if you calculate QCA, and since it's a compression, QCA is delta U minus W. This is via first law of thermodynamics. So delta U is NCV delta T minus work done. And if you clearly see the temperature, the change in temperature here is the temperature at A is T1 and temperature at C is T2. So the difference is T1 minus T2. And according to question, it's given 1 mole of a monoatomic gas. So N is 1, and for monoatomic gas CV is 3 by 2 R, and temperature is T1 minus T2, and work done from C to A that we have calculated here is P naught V naught minus P naught V naught. So 3 by 2 RT1 minus RT2 minus P naught V naught, and RT1 can be written as P1 V1 by 1, that is mole is 1, minus P2 V2 minus P0 V0. And if you clearly see at temperature T1, pressure is P0 and volume is V0. So we can write this as 3 by 2 P0 V0 minus, at 2 the pressure is P0 and volume is V0. That is P0 twice of V0 minus P0 V0. So on further simplification, you will get minus 3 by 2 P0 V0 minus P0 V0, that is minus 5 by 2 P0 V0. So the net heat rejected by the system, that is heat given by the system, that is considered as negative. So QCA is completely 5 by 2 P0 V0. And the second part of the B question, the heat absorbed by the gas in the path AB. If you see the path A to B, it's clearly an isochoric path in which work done would be 0. If you see QAB, that would be equal to delta U, because work done is 0, because it's an isochoric process. And delta U is N CV, change in temperature. And as we move from A to B, temperature varies from T1 to T2. So N is 1, CV is 3 by 2 R for a monoatomic ideal gas, and delta T is T1 minus T2. And if you see at temperature T1, here the pressure is P0, volume is V0. So 3 by 2 RT1 minus RT2. So 3 by 2 RT1 can be written as P0 V0 by moles, that is 1, and RT2 can be written as, at temperature T2 the pressure is 3 P0 and volume is V0. So RT2 can be written as 3 P0 V0. So on further simplification, you will have minus 3 P0 V0. So the heat absorbed by the gas in the path AB, that is QAB, is minus 3 P0 V0. So this is the answer for the part B of the question. The heat rejected in the process C2A is minus 5 by 2 P0 V0, and the heat rejected and the heat absorbed in the path A to B is minus 3 P0 V0. Coming to the third part, the net heat absorbed by the gas in the path B to C. If we see the path B to C, it's clearly an isothermal in nature, because the temperature at B is also T0 and the temperature C is also T0. So in that case, in the C part, QBC would be equal to minus of work done, because delta U is 0 since it's an isothermal condition. And clearly when you move from B to C, the area under the curve will give you the work done, and we have already calculated the work done in path BC here, that is minus 2 P0 V0. So if you put that here, minus minus becomes positive, QBC is 2 P0 V0. Now moving to the last part of the question, that is the maximum temperature attained by the gas during the cycle. So firstly we need to find the relation between the given temperatures in this graph, that is T1 and T2. We need to find the relation between the temperature, and whoever is greater, either T1 or T2, will be the maximum temperature attained by the gas during the cycle. So if you see the path AB, it's an isochoric path because it is happening at the constant volume. So if you see in the path A to B, if you see in path A to B, if you clearly see It's an isochoric process, so we can write in the option D, path AB is isochoric. Therefore, volume at A must be equal to volume at B, and volume at A can be written as nRTA by PA is equals to nRTB by PB. And if you see, the temperature at A is T1 and pressure is P naught, and temperature at B is T2 and pressure is 3 P naught. So putting that in this equation, we'll have N gets cancelled on both sides, R also gets cancelled. So TA is T1, PA is P naught, TB is T naught, PB is 3 P naught. So T2 is 3 times T1, and T1 can be written as P naught V naught by R. So the maximum temperature attained in the cycle is T equals T2, and that is indeed 3 P naught V naught by R. So this is the complete solution of this question and all four parts.
Hello, we are given with a question, and the question says a sample of 2 kg monoatomic helium is taken from A to C from this way, and same mass is taken from C to A. That is another sample. Given molecular mass of helium is 4 gram. So we are given that the molecular mass is 4 grams. Right? So what is the temperature of helium at each state? So using the ideal gas equation, that is PV equal to nRT, right? So N would be equal to the mass that is given 2 into 10 to the power 3 by the molecular mass, that is 4. So it turns out to be equal to 500 moles, right? So using this ideal gas equation in first question, the temperature at A would be equal to PA VA by NR. So from there, it would turn out to be equal to, when we substituted the value, PA is 5 into 10, right? That is 5 into 10 to the power 4. So we can write 5 into 10 to the power 4 into 10 divided by 500 into the value 8.31. Right, so this TA would be equal to 120.33 Kelvin approximately. Right, now similarly, when we find TB, that is equal to PB VB by NR, so that turns out to be equal to 240.66 Kelvin. TC similarly turned out to be equal to 481.32 Kelvin, and TD turned out to be equal to 240.66 Kelvin. Right. So from here, what we can say is that these are the temperatures, right? The next question. Is there any way of telling afterwards which sample of helium went through the process ABC and which went through the process ADC? Right? We are taking it from ADC. So, is it possible to tell that which is going from where? No, obviously not, right? Because the final state of the gas is same and the amount of gas present is even same. So it is not possible for us to differentiate. So the answer is no. Now the third question, right? The third question is, how much is the heat involved in the process ABC and ADC? Right? So how much is the work done? How much is the heat involved, right? So from here, since in process ABC, right, what we can say is that delta U would be equal to NCV delta T, right? Since we are provided with the monoatomic helium gas, so CV would be 3 by 2R. So the N number of moles is 500 into 3 by 2 into 8.31 into delta T. So what would be delta T? So delta T in ABC is THC, that is 481 minus T at A, right? So it would be 481.32 minus 120.33. So this would turn out to be equal to 2.25 into 10 to power 6 joules. So this is the value that we get from ABC, right? So the work done would be equal to the area under this graph. So this whole, right? So that would be equal to, since the difference is 10 and this is also 10, right? So 10 into 10 into 10 to power 4. So that would be equal to 10 to power 6 joules, right? So the according to the first law, delta Q would be equal to delta U plus uh, delta U plus W. So that would be equal to, obviously, that would be equal to 2.25 plus 1, right? So that is 3.25 into 10 to power 6 joules, right? So now, since we have this in ABC, right? So for now, ADC process, the amount of delta U in ADC, right? So delta U would be equal to, since we have final temperature to be equal to 481, right? And initial was 120. So the delta U would be same as that of ABC. So that is 2.25 into 10 to power 6 joules, right? Now the work done, that is the area under the curve, would only be this much. We would have this area, ADC, this area, right? So that will be equal to 5 into 10 to power 4 into 20 minus 10, so that is 10. So 5 into 10 into 10 to power 4. So this value turns out to be equal to 0.5 into 10 to power 6 joules, right? So when we use the first law, so this was in ABC, this is in ADC. So that turns out to be equal to 2.75 into 10 to power 6 joules, right? So the amount of heat involved in ABC is greater than ADC, right? And this is the amount that we found out. So this is the answer of this whole question. Thank you.
Hello everyone. So we are given with the question which says 1 mole of diatomic ideal gas having a adiabatic index as 1.4 is taken through a cyclic process starting from point A. The process AB is adiabatic compression, BC is isobaric expansion, CD is an adiabatic expansion, and D2A is isochoric process. The volume ratios is been given VA by VB at 16, VC by VB as 2, and the temperature at A is 300 Kelvin. We need to calculate the temperature of the gas at point B and D, and also we need to find the efficiency of the cycle. So first let's try to calculate the temperature at B and D. So the given scenario something looks like this, and as we can have a look over here, A to B is adiabatic compression, B to C is isobaric, so pressure has to be constant. So B to C, C to D is again adiabatic expansion, and D to A is isochoric, means it is a isochoric process. Now we have to calculate temperature of at point B and temperature at point D. All right. So since A to B is an adiabatic process, we can say for adiabatic the relation, the process equation is PV raised to gamma, and that is equals to constant. and we can write, instead of P we can write nRT by V. So instead of P we can write nRT upon V into V raised to gamma, and that is equals to constant. Since it's an ideal gas, so equation PV is equals to nRT holds true over here. Therefore from here we can say T into V raised to gamma minus 1 will be a constant. Alright, or we can say will be a new constant, but it's a constant value. Now as we have got the relation, so we can develop apply this equation. Let's say this is our equation 1 in the process A to B and C to D. Therefore we can get, so we can write from this, we can say TB upon TA, and that would be equals to VA upon VB. Since the relation is inverse over here, that's why we are writing we are following the inverse relation. All right, now from here we have been given with the ratio of VA by VB, and so we will substitute this value and we will get the value of TB. Therefore TA into this value, that is we can write TB, TB will be TA, that is 300 into VA by VB is 16 raised to 0.4. all right, so this value comes out to be, 909 Kelvin. So we have calculated the temperature at B. Now we have to calculate the same process we will follow for the C to D process. We can write TD by TC, that can be written as VC by VD, the whole raised to gamma minus 1. But before that we have to check whether we have been given with VC by VD. No, so we have to first calculate the value of VD, then we can apply this equation. So we proceed such a way that, so for this we have to first consider that we have been given with let's say VA by VB as to be 16, and we have been given with the ratio of VC by VB, VC by VB as it's been given to be as 2. So therefore we can get the value of VA upon VC, that is equals to 8. And if we carefully analyze the given diagram, so point D and A both will have the same volume as the process is isochoric, so we can write VD by VC will also be 8. So this is just for the understanding we have written. Therefore we can write here it is the reasoning type. So we can say TD will be equals to TC into VC by VD will be nothing but 1 over 8 and raised to 0.4, and that comes out to be the value of TC is if we have a careful look, so the value of TC, that is this value. Now to calculate TC, first let's say we can have at pressure P, pressure at B and pressure at C is equal, as the process is isobaric from B to C. Therefore we can write this can be written as VB by TB, and that is equals to VC by TC. Alright, therefore from here we can say the value of TC can be written as VC by VB into TB, VC by VB into TB. Alright, and the temperature of TB we have calculated as 909, so it can be written as 909 into VC by VB. The ratio has been given to be as 2. So this value comes out to be 1818 Kelvin. Alright, so this is also an reasoning for just we will use TC as 1818 into 1 by 8 raised to 0.4, and this value comes out to be, therefore we can say the value of TD comes out to be or we will just directly substitute it over here. So instead of Tc we will write it as 1818, and solving this value we will get the answer as 791. So 791 Kelvin. So the temperature at point D will be 791 Kelvin, and at TB it is 909 Kelvin. Alright. So this is the first part of the question. Let's now move on to the second part, in which we have to find the efficiency of the cycle. So we can write it as efficiency, that is eta, denoted by eta. So let's take over. Okay. So eta can be written as total work done or net work done upon heat supplied. Okay. So and into 100. So this is the formula for efficiency. So we have to calculate first heat supplied, that is QS. So as we can see in the diagram, A to B is an adiabatic process and C to D is again an adiabatic process. So heat will be supplied during this process, so the expansion will take place. So here it is heat supplied, and from here the heat has been rejected. Alright, so this is QR. So since heat supplied is during the isobaric process, so we will write it as heat supplied will be nothing but it is N CPDT. Alright, or this can be written as N, that is number of moles is being given to be as 1, so we can write it as Cp dt. Dt will be Tc minus of Tb. Alright, so here we can write Cp can be written as since we know the relation, that is Mayer's relation, Cp minus Cv is equals to R, and we know Cp by Cv is equals to the adiabatic index. From here we can say instead of Cp we can write write R gamma upon gamma minus 1, that is adiabatic index minus 1, that into Tc minus of Tb. Alright, so solving this value, 1.4 divided by 0.4 into R, and Tc we have been given with Tc we have calculated it as 1818, and Tb is 909. So 1818 minus 909, and that would comes out to be approximately 3182 R. Alright, so this is the value of heat supplied we have calculated. Now we have to calculate the work done. So net work done, that is we have to, now we can say W net is nothing but work done from A to B plus of work done from B to C plus of work done from C to D, and finally work done from D to A. So we have to calculate all the 4 work done, and we have to just add them up, so we will get net work done. So from here we can write WAB, that is A to B is an isothermal, A to B is an adiabatic compression. So from here we can see the formula can be written as, for adiabatic process work done formula is we can write it as Cv into Tb minus of Ta. So this is the work done formula in case of an adiabatic process. Alright, so Cv can be written as we can write it as R by 1 minus gamma. In terms of adiabatic index we are writing this is Tb minus Ta. So we have to just substitute the value, and 1 minus that is it comes out to be negative value, that is negative of we can say it as R by 0.4 into Tb is been given to we have calculated it as 909 minus of Ta is 300. So this value comes out to be this can be written as 2 by 5, so it becomes 5 by 2 R into 609 joules. So this is the work done from A to B. Calculate now work done from B to C, and that can be written as, since B to C is an isobaric process, so we can write it as work done can be written as P delta V in this case. Now this formula can be further modified as NR delta T. Alright, so this can be written as, since it's 1 mole, so R delta T, that is Tc minus of Tb, and Tc we have calculated it as, the value of Tc is 1818, and Td value is the value of Td is 791. So we can write here as R into Tc value is 1818 minus of value of Tb is 909. Alright, so this value comes out to be 909 R. Alright, so let's check once again. The value of TB is 909. Okay, so let's proceed further. So this is the work done from B to C. Now we have to calculate work done from C to D. That is again an that is again an adiabatic expansion process. So we will be using the formula as CV into TD minus of TC. Again we can write instead of CV, this can be written as R upon 1 minus of gamma, and it can be written as TD minus of TC. Alright, so this value is coming out to be negative 5 by 2 R into TD is being calculated as 791 and TC is 1818. So 791 minus of 18 and 18, so this value on solving gives us the answer as plus of pi by 2 R into 1027 joules. Alright, so this is the value of work done we are getting from C to D, 1027 joules. Alright, so now we have to finally calculate the work done from D to A. Therefore we can write work done from D to A. Since it's an isochoric process, so work done will be 0, since we can write P delta V is the work done, and delta V is 0. That is, for isochoric process there is no change in volume, therefore work done is 0. Therefore now we can write net work done can be written as, we have got WAB as minus 5 by 2 R 609 minus of pi by 2 R into 609 plus of A to B, B to C is 909 R, 909 R, and plus of this is pi by 2 R into 1027. So solving this value, we will get 909 R plus of, and this is 1, we can write it as 1045 into R, and while adding this to, we will get the answer as 1954 R joules. So this is the total net work done we have calculated. We have just kept the value of R as it is everywhere, because we are trying to avoid the decimal part. So now we can easily calculate the efficiency, which is nothing but W net upon heat supplied, and that into 100. So we can write it as W net, we have calculated the value as 1954 R divided by heat supplied, can be we have calculated 3182 3182 R. Alright, so from here we can divide both of this, and we will get the answer as efficiency in terms of percent. We will get it as, this is here, it is into 100. So this value comes out to be, solving this value comes out to 0.61 into 100, that is 61.4%. So this is the efficiency of this complete cycle. So I hope you have understood the concept, and thank you for watching.
Hello everyone, so the question is at 27 degrees centigrade, 2 moles of an ideal monoatomic gas occupy a volume V. The gas expands adiabatically to a volume 2V. Adiabatically, okay. Now calculate the final temperature of the gas, change in its internal energy and the work done by the gas during this process. Now in the question they are saying that the process is adiabatically, and in adiabatic process the relation between the temperature and volume is given by the equation Tv gamma minus 1 equals to constant, and the initial volume is given in the question which is V, and final volume is also given in the question which is 2V, and the initial temperature is equals to the 27 degrees centigrade, or I can change it into Kelvin, so it is 300 Kelvin, and we have to find out the final temperature of the gas. Okay, so I am going to apply this equation for the initial and final situation. So it is T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1. The value of T1 is 300. V gamma minus 1 equals to T2 2V gamma minus 1. So V gamma minus 1, V gamma minus 1 is cancel out. So the value of T2 is coming out to be 300 upon 2 gamma minus 1. And I can also write this as 2 1 minus gamma 300 Kelvin. So this is the final temperature of the gas. This is the first part. Okay, and in second part they are saying to calculate the change in internal energy. Okay, the internal energy is given by the formula delta U, which is my change in internal energy, is given by NCV delta T. Now gas is monatomic, and for monatomic gas the value of CV is 3 by 2R. Putting the value delta U equals to 3 by 2 N R. N is number of mole, delta T is temperature difference. Okay, so it is final temperature minus initial temperature, and final temperature after calculating this value I will get my final temperature as 189 Kelvin. Okay, so the change in temperature can be written as 189 minus 300. 189 minus 300. Number of moles is also given in the question, which is 1 mole 3 by 2 into 1 into value of R is 8.314 into 189 minus 300. The value comes in negative, and which is equal to minus 21. Okay, after solving this, finally we will get the value delta U equals to, sorry, it's 111. Okay, when we calculate 189 minus 300, so it is coming out to be negative 111. Okay, the value is minus 111. Now solving this, we will finally get my internal energy, that is comes out to be minus 2767 joule. Okay, so this is my change in internal energy. And in the third part they are saying to calculate the work done by the gas. Okay, so from thermodynamics first law we know that the heat given to the gas is equal to the change in internal energy plus work done. Now the process is adiabatic, and for adiabatic process the heat is zero because there is no heat exchange between the system and surrounding. So in that case my delta U equals to the minus W, or I can say W equals to minus delta U, and I already calculated the value of change in internal energy, so my work done is equals to the minus minus plus, so it is 2767 joule. This is my work done for this process. Okay, thank you.
तो क्वेश्चन में हमें क्या गिवन है, एन आइडियल गैस इज टेकन थ्रू अ साइक्लिक थर्मोडायनेमिक प्रोसेस थ्रू 4 स्टेप। तो एक आइडियल गैस है जिसको हम एक थर्मोडायनेमिक प्रोसेस के अंडर मूव करवा रहे हैं थ्रू 4 स्टेप्स। ओके, द अमाउंट्स ऑफ हीट इन्वॉल्व्ड इन दीज स्टेप्स आर Q1, Q2, Q3 and Q4. The corresponding quantities of work involved are W1, W2, and W3 or W4. Okay, so in first part I have to calculate value of W4 and in second part we have to calculate efficiency of the cycle. ओके तो चार पाथ हैं. ओके तो चारों पाथ की क्यू मेरे को गिवन है, चारों पाथ में हीट इन्वॉल्व गिवन है, तीन पार्ट में वर्क इन्वॉल्व गिवन है और चौथे पार्ट में मेरे को वर्क इन्वॉल्व कैलकुलेट करना है. ओके तो सबसे पहले क्यू की साइक्लिक प्रोसेस है, तो साइक्लिक प्रोसेस में डेल्टा यू क्या होगा, जीरो, क्योंकि यू एक स्टेट फंक्शन है. तो साइक्लिक प्रोसेस में डेल्टा यू क्या हो जाएगा, जीरो हो जाएगा. तो यूजिंग फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स आई कैन राइट डेल्टा यू इज इक्वल टू क्यू माइनस डब्ल्यू. दिस गिव्स मी Q is equal to W as work delta U is 0. So I can write Q1 plus Q2 plus Q3 plus Q4 is equal to W1 plus W2 plus W3 and plus W4. Okay, so I have to just put the values from the question where Q1 is 5960, so I will put here 5960. Q2, what is the value of Q2? It is minus 5585. What is the value of Q3? It is minus 2980. And what is the value of Q4? It is plus 3645, which is equal to W1. What is the value of W1? 2200. W2 is minus 825. W3 is minus 1100 plus W4. ओके सो ऑन तो सॉल्व करने के बाद हमारे पास W4 की वैल्यू कितनी आ जाती है, 765 जूल्स. ओके तो यहाँ पे हमारे पास फर्स्ट पार्ट का सॉल्यूशन आ गया 765 जूल का है. और सेकंड पार्ट में हमें एफिशिएंसी पूछी हुई है, तो सबसे पहले मैं क्या करूँगा, एफिशिएंसी का फॉर्मूला लिखूंगा. एफिशिएंसी का फॉर्मूला क्या होता है, टोटल वर्क डन divided by heat absorbed. Okay, so total work done divided by heat absorbed multiplied by 100 is equal to not, so it will be equal to W1 plus W2 plus W3 plus W4 होल डिवाइडेड बाय हीट एब्जॉर्ब. लिखते वक्त ध्यान रखना है कि यहाँ पे सिर्फ हमें पॉजिटिव हीट मेंशन करनी है, Q1 प्लस Q4. अब यहाँ पे सिर्फ पॉजिटिव हीट क्यों मेंशन की, बिकॉज जो नेगेटिव हीट्स हैं वो हीट्स गैस ने एब्जॉर्ब नहीं की, वो इवॉल्व की है. हमें यहाँ पे क्या मेंशन करना है, सिर्फ हीट एब्जॉर्ब, तो इसीलिए हम क्या लिखेंगे, पॉजिटिव हीट्स ओनली. ओके और इसको हम मल्टीप्लाई कर देंगे 100 से. नाउ पुटिंग द वैल्यूज आई गेट नीटा एज W1 is 2200, W2 is minus 825, W3 is minus 1100, W4 I have calculated 765 divided by Q1 plus Q4. Now Q1 is 5960 plus 3645. Okay, now I have to also multiply with 100, so I will get 1040 divided by 9605 into 100, so it will be 10.82%. okay, so it's our final efficiency, that is 10.82%. thank you.
1 mole of a monoatomic ideal gas is taken through the cycle in the figure. A to B adiabatic expansion, B to C cooling at constant volume, C to D adiabatic expression, D to A heating at constant volume. The pressure and temperature at point A and B etc. denoted by these all respectively, given that TA is equal to 1000 K, PB is equal to 2 by third part of PA, PC is equal to PA by 3. Calculate the following. So at the first we have to calculate the work done by the gas in the process A to B. Second part is the heat lost by the gas in the process B to C and the temperature at point D. And given that 2 by 3 raised to power 2 by 5 is equal to 0.85, and this is our the diagram. So at the first we'll write down all the quantities which are given So such that at the first we know that given that Ta is equal to 1000 K, 1000 Kelvin, and N is equal to 1. Number of moles are given 1. And we know that PV is equal to 2 by 3 of PA. After that, if we know that gas is monoatomic gas, so gamma will be 5 by 3. Gamma is Poisson ratio. And PC is equal to PA by 3, or we can say that 1 by 3 into PA. And one more thing is given that is very important. 2 by 3 whole raised to power 2 by 5 is equal to 0.85. These are all the given elements. So at the first, if we talk about the process A to B, so A to B is the adiabatic process, and the equation of state for adiabatic process is T is raised to power 1 minus gamma into T raised to power gamma is equal to T raised to power 1 minus gamma into T raised to power gamma at point A and point B respectively. After that, if we have to calculate the value of TB, so how will we calculate the value of TB? So TB must be written as TA into PA divided by PB power 1 minus gamma divided by gamma is equal to, as we know that TA is given that TA is 1000 Kelvin, TA is 1000 Kelvin, and what about PA and PB? So PA is PA upon PB is equal to 3 by 2. So 3 by 2, and if we solve this equation 1 minus gamma upon gamma, and gamma is 5 by 3, if we solve this we can get minus 2 by 5. So if we solve this equation we can get 1000 into 0.85, because the value of this expression 2 by 3 power 2 by 5 is equal to 0.85, so we multiply it and we can get 850 Kelvin. So this is the temperature at point B. Okay. After this all, if we talk about the process B2C, so if we talk about the process B2C, so B2C is a isochoric process. So we can write this PV by ideal gas equation, PV upon TV is equal to PC divided by TC. As we know that in this state, volume must be is equal to 0, change in volume must be equal to 0, because B2C is a isochoric process. In isochoric process, change in volume must be equal to 0. So by the ideal gas equation, we can write PV upon TV is equal to PC upon TC. So we can find TC from this equation. TC is equal to PC into TB divided by PB. So put the value of these elements 850 into and PC upon PB. What is PC upon PB? That is 1 by 2. So we can get TC is equal to 425 Kelvin. 425 Kelvin. Okay, after that, if we have to find the work done from A to B process, so work done from A to B process, that will be NR TA minus TB, NR TA minus TB divided by gamma minus 1. That is the work done in adiabatic process, the formula for work done in adiabatic process. So N is 1 and the value of R means gas constant, that is 8.134, and the temperature or TA is given 1000 Kelvin, and TB we have calculated TB as 850 Kelvin divided by what is gamma? 5 by 3 minus 1. For monatomic gas, gamma is 5 by 3. So if we solve this equation, we can find 1870.2 joule. This is the work done in AB process. Okay. After this all, if we find delta Q, in process BC, so we can say that delta U plus delta W. This is first law of thermodynamics. So delta U from B2C process and delta W from B2C process. And in B2C process, work done will be 0 because change in volume is equal to 0. That is isoporic process. And delta U, what about delta U? So we can write this as N CV delta T. N CV delta T. That is equal to 3 by 2R. That is equal to 3 by 2R. And what about the temperature difference? TC minus TB. Because the process is from B to C, so temperature change will be TC minus TB. Okay. Now, if we solve this all, so N is equal to 1, 3 by 2. R is gas constant, that is 8.134. After that, change in temperature will be 425 minus 850. 850. Okay, so if we solve this equation, we get minus 5300.17 joule. We can get this equation. Okay. After this, for A to B process, let me change the inkle. Okay. So if we talk about the A to B process, so A to B process, PA, equation of state is PAVA raised to power gamma is equal to PBVB raised to power gamma. So we can write this equation such as VA upon VB whole power gamma is equal to V upon VB whole power gamma is equal to PV divided by PA. After this all, we can say that PA divided by PV is equal to 3 upon 2. Put the values of these terms in this equation. We can solve this. So we can find PA upon PV is equal to 3 by 2. Okay. After this all, if we talk about process C to D, so we can say that equation of state must be PCVC raised to power gamma is equal to PD VD raised to power gamma. So we can write this equation such as VC upon VD whole power gamma is equal to VB divided by VD. VB divided by VA whole power gamma. We have compared these two equations. We can find this equation. So it will become 3 by 2 is equal to PD divided by PC. So we can say that PD is equal to 3 by 2 into PC. So PD is equal to 3 by 2 into PC. After that, at end point, A and D, these are the endpoints. So equation of state must be PA upon TA is equal to PD divided by TD. So put the values of PA, that is 3 PC, divided by temperature at TA is 1000 Kelvin, that is given in the question. What about PD? PD is 3 by 2 PC and divided by TD. So from this equation we can solve. We can find the value of TD. PC and PC are cancelled out. 3 and 3 are cancelled out. So we can find this TD from this equation, that is 500 Kelvin. So these are all the answers. And what about the work done from point B to C? So work done from point B to C will be is equal to 0. And why the work done from point B to C will be is equal to 0? Because from B to C, that is isochoric process, and in isochoric process delta V is equal to 0, change in volume is equal to 0. So if change in volume is equal to 0, so we can say that work done in isochoric process is also 0. So these are all our answers.
Hello. The question says that 3 moles of an ideal gas which was at pressure Pa and temperature Ta is isothermally expanded to twice its initial volume. So let us assume that the first state be A, the second state be B. Okay, so initially it was having pressure Pa, temperature Ta, and suppose the volume will be Va. Okay, so what has happened here, that it has been expanded isothermally. So in isothermal we know that the temperature will remain same, okay, and the volume has become twice, so it will be twice of Va. Okay, and the pressure here will, let us assume it to be Pv. Okay, and it is then compressed at a constant pressure to its original volume. Okay, so constant pressure, that means Pb will remain same and the volume will to its original volume, then the volume will become Va. Okay, and then the temperature, let it be at Tc. Finally gas is compressed at constant volume to its original pressure Pa. So constant volume, and this will be like constant volume and pressure, original pressure Pa. So the pressure will become Pa and volume will become Va. So this will become, the C part will, the next step will be A. Okay, so that it will be a complete cycle. Okay, so so this original to pressure is Pa. Okay, so this has become the complete cycle. Now let us see the process AB. So as it is given, isothermal, so this means constant temperature, as I have already written, constant temperature. This implies Tb is equal to Ta. Okay, so I have written the same. So from here, as it is an isothermal process, we can say that Pa Va will be equal to Pb Vb, right? So this implies Pa into Va equal to Pb. Vb is twice of Va, so Va. So this implies Pb is equal to Pa by 2. Okay, so now for process BC, that is the second process, it has given us that constant pressure, so that means it will be a isobaric. Okay, so this implies that Pb will be equal to Pc, which I have already written, that Pb here. Okay, so from here we can see that Vb over Tb will be equal to, as it is isobaric, equal to Vc over Tc. So this implies Vb is given as twice of Va, so twice of Va over Tb is nothing but Ta. Ta is equal to Vc. Vc is again Va over Tc, so let it be Tc. Okay, so from here we can see that this implies Tc is equal to Ta by 2, right? So now for the process C2A, so this has given us constant volume, that means it is isochoric, so that means constant volume. Okay, so from here we can say that Pc over Tc will be equal to Pa over Ta, right? So from here, as we know, Pc is equal to Pb. Okay, as we know, Pc is equal to Pb, which I have already written here also. Okay, which is equal to Pa by 2, right? So what we can write here is this Pc is Pa by 2, so this means Pa by 2 Tc equal to Pa by Ta, right? PA got cancelled. This implies TC is equal to TA by 2, right? So now we have all these positions or the coordinates of the T graph, right? So what we can write is like in order to draw the graph, suppose we have to draw this PV graph, right? Suppose this is P, this is V. As we know that A to B is isothermal process. So isothermal process is something like rectangular hyperbola. It will be like this, okay, A to B, because we can see that at B the volume is double, okay, the volume is, where is the volume, VA is twice of VA, C. So this will be like 2 VA and this is VA, right? And the pressure here, suppose it is PA, so the pressure here is PB, okay, and this is like isobaric, so pressure is constant, and then it is isochoric, this volume is this, so it will go like A to B, B to C, then C to A. So this is it, this is its PV graph, right? Now for PT graph, okay, suppose this is P and this is T, okay, so what is happening, A to B, A to B is isothermal, that means temperature is constant, and B to C is baric isobaric, that means pressure is constant, and then it will be like isochoric or like this, okay. So here it will be A, B and C, A to B, B to C, C to A, okay. So these two both are like we can see that this is cyclic, okay. So now for, as I've said, work done will be W of AB plus W of BC plus W of CA, right? So for AB, as I've said, we have seen here that it is a isothermal, so it will be NRTA ln VB over VA, right? And for this BC, it will be NR TC minus TA, right? And for and for C2A this will be 0, right? So by calculating this, we can write here as 2.303 because it is ln, so converting into log, it will be 2.303 into n is 3 number of moles into R into TA into log of base 10, VB is twice of VA upon VA, correct? So this will be log 2 only, plus 3R, TC is nothing but TA by 2, we have already seen, minus TA, correct? So if we solve this, what we will get, this TA minus will be nothing but minus TA by 2, okay. So after solving, we will get this 0.58 R into TA, okay. This V will get cancelled, this TA will remain, and here also RTA, so the work done will be same, okay. So now it is also asking, the question is also asking us about calculate the work done and the net heat supplied to the gas during the complete process. So obviously, as the work done is 0.58 RTA, so the heat supplied will be Q is equal to 0.58 RTA, because this is a cyclic process, delta U will be 0, and from the equation dW is equal to dQ plus du, this is 0, dW will be equal to dQ only. So this is the answer. Thank you.
Hi everyone, so we are given with a question which says we need to calculate the work done when 1 mole of perfect gas is compressed adiabatically The initial pressure and volume of the gas has been given as 10 raised to 5 Newton per meter square and 6 liter respectively. The final volume of the gas are 2 liter. Molar specific heat of a gas at constant volume is 3R by 2. So we have to calculate work done in adiabatic process. So we can write for adiabatic process, we know the relation, that is PV raised to gamma is a constant. Here gamma is nothing but it is the refractive index, or it is the adiabatic index. So we can say from here, first we have to calculate this value of adiabatic index. Before that we can write this expression in this way, that is P initial V initial raised to gamma, that is pressure volume raised to gamma, and that is equals to P final pressure into final volume raised to gamma. Alright, and now we can say this is, let's say, our expression number 1. Now of adiabatic index, that is gamma, is can be written as, it is a ratio of molar specific heat capacity at constant pressure upon molar specific heat at constant volume. So from here we have been given with molar specific heat at constant volume 3R by 2. Therefore we can get the value of so now we can use Mayer's relation that says Cp minus Cv is equals to R. From here we can get the value of Cp. Therefore from here we can say Cp will be equals to R plus Cv. So it comes out to be 5R by 2, since we have been given with molar specific heat at constant volume as 3R by 2. Alright, and this is what the Mayer's relation is. So we can keep it a note over here. Mayer's relation. Alright, so from here we can say the value of adiabatic index which we are getting will be, we just have to take the ratio of Cp and Cv. Therefore we can say gamma comes out to be 5R by 2 divided by 3R by 2. So this comes out to be 5 by 3. Alright, now what we can do over here is, we have with us the value of gamma, that is adiabatic index, and so we can say work done formula can be now written as, therefore work done in adiabatic process is given by the formula, that is W equals to P Pi Vi minus Pf Vf dividing by, or we can write this way. So this can be written as initial pressure into initial volume minus final pressure into final volume dividing by gamma minus 1. So if you substitute all the respective values that has been given, that is we have with us Pi, Vi, and we have with us final volume, but we don't have final pressure. So from equation 1 we can first calculate the value of final pressure, then we will substitute in this expression. So let's say this is our equation number 2. From 1 we can write final pressure Pf can be written as, we can clearly see from it, Pi into Vi by Vf raised to gamma. Alright, so from here we can say if we substitute the values over here, so we can write final volume, final initial pressure has been given as 10 raised to 5. So we will substitute it over here, 10 raised to 5 into initial volume has been given as 6 liters and final is 2 liters. So 6 by 2. So that becomes 3 over here and gamma is 5 by 3. So this result comes out to be 10 raised to 5 into 3 raised to 5 by 3. So this is what the result we are getting for final pressure. So now we can substitute it in equation 2. So we can write from equation 2 now work done can be written as Pi, that is 10 raised to 5 into initial volume 6 liters, converting it into meter cube, so 10 raised to minus 3. So this is PIVI minus PF. Just we have calculated now. PF is 3 raised to 5 by 3 into 10 raised to 5. Final volume is given as 2 liters, that is 2 into 10 raised to minus 3 meter cube, dividing by gamma minus 1. That is 5 by 3 minus 1. So here we can write it as 3 by 2 into 10 raised to 2, and here we can write 6 minus of what we are left with inside is 12.48. After multiplying 3 raised to 5 by 3 into 2, we are getting 12.8. So final answer comes out to be minus of 972 joules. Alright, so this is the work done we are getting for this adiabatic process. So I hope you have understood the concept, and thank you for.
इस क्वेश्चन में हमको वीटी कर्व गिवन है और इसको हमें पीवी कर्व में ट्रांसफ़र करना है। तो हम तीनों प्रोसेस कंसिडर करेंगे, पहले ए बी करेंगे, फिर बी सी करेंगे, फिर सी ए करेंगे, फिर देखेंगे कैसा इसका रेस्पॉन्स आता है। तो पहले ए बी करते हैं, ए बी प्रोसेस। देखो ए बी प्रोसेस ओरिजिन से पास हो रहा है, इसका मतलब जो इसकी इक्वेशन होगी वो होगी v इक्वल्स टू एम टाइम्स टी। एम इसका स्लोप है लाइन का, तो हम इसको एट एज इक्वेशन में डालते हैं, पी वी इक्वल्स टू एन आर टी। टी कैंसिल हो जाएगा तो पी आएगा हमारा एन आर बाई एम। एन कॉन्स्टेंट है क्योंकि हमको कॉन्स्टेंट मास दिया हुआ है, आर गैस कॉन्स्टेंट है और एम स्लोप है वो भी कॉन्स्टेंट है, तो पी आ गया हमारा कॉन्स्टेंट। ठीक है, अब यहाँ पर हम एक पीवी कर्व बना देते हैं। तो पी कांस्टेंट आएगा फर्स्ट इक्वेशन में वी बढ़ाने पर, तो हम मानते हैं कि ये ऐसे आएगा ए बी। ठीक है, अब बी सी प्रोसेस कंसिडर करते हैं। बी सी प्रोसेस में हमको दिख रहा है कि वी कांस्टेंट है। ठीक है, तो आइडियल गैस इक्वेशन देखते हैं, पी वी इक्वल्स टू एन आर टी। तो P इक्वल्स टू एन आर टी बाई वी। तो P इज डायरेक्टली प्रोपोर्शनल टू T बिकॉज N R एंड V आर कॉन्स्टेंट। अब देखो BC प्रोसेस में टेम्परेचर डिक्रीज हो रहा है और हमने फाइंड किया कि P इज डायरेक्टली प्रोपोर्शनल टू T, तो प्रेशर भी डिक्रीज होगा, तो PC प्लॉट आएगा ऐसे, प्रेशर डिक्रीज होता होगा कांस्टेंट वॉल्यूम पर। इसे मान लेते हैं हम C। अब कंसिडर करते हैं CA प्रोसेस। CA प्रोसेस में T कांस्टेंट है। ठीक है, तो PV इक्वल्स टू NRT। इसका मतलब हुआ कि NR और T कांस्टेंट है तो PV इक्वल्स टू कांस्टेंट हो गया, तो एक हाइपरबोला बनेगा इस तरह से। तो ये ऐसे बनेगा AB BC CA।